So at long last, we finally get to cover our quadratic formula. So our quadratic formula is the catch-all method to find the roots of any quadratic. So before, we've been trying to find the roots. It is where the parabolas cross the x-axis. Every quadratic has two roots, and there are three types of roots. So the first type, the parabola curves up, could possibly curve down, doesn't matter, and it crosses the x-axis in two distinct places. These are called two real roots. The second type, the parabola just comes down and only the vertex hits the x-axis right here. This is called a double root. Both roots are the exact same. And last but not least, parabola does not cross the x-axis at all. These are imaginary roots, or for us, no real roots. So before, we have been finding the roots either by graphing and then estimating, or by factoring. The problem is there are many quadratics that can't be factored, and I don't want to graph all of these to figure out the answer. One technique we're going to learn next week, completing the square, can help us as well. Kind of goes back to solving vertex form. Completing the square helps us take quadratics from standard form into vertex form. But the one method that works regardless of the quadratic is quadratic formula. I'm going to show you kind of how the quadratic formula came to be. You do not need to know how to do this. It is very weird looking. This is using the completing the square technique with no numbers, just our variables. So we have our standard form quadratic, ax squared plus bx plus c is equal to 0, because that's where we find the roots, is when the y value equals 0. And what's happening is we're going to start to do the completing the square method. We get just these x terms on the left. We divide by can't have a leading coefficient. We're going to get a new term like this. This is a perfect square trinomial, and that's how we get to this. Perfect square trinomial. Then convert this to be over 4a squared. We square root both sides, that's how we get the plus or minus. We have x plus b over 2a. Subtract that because it's over the same coefficient, we can put it together. And that brings us to our quadratic formula. This, in all its glory, is the quadratic formula. This will help you find the roots to any quadratic as long as it's in standard form. It does have a song. It goes to the tune of Pop Goes the Weasel. And it goes a little something like this. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So the big thing about our quadratic formula is it has to be standard form. So let's take this quadratic. It is equal to 0, so we're good to go. Honestly, we could factor this one. If we factor it, I need two numbers that multiply to 6 to add to 7, 1 and 6. Using our shortcut, we get this, so our answers are negative 6, negative 1. But we're going to use our quadratic formula to help us prove that this is the case. Because not all quadratics are factorable. We have to be able to use our quadratic formula to help us. Do not think you're smarter than the quadratic formula. Write it down every time you use it. Do not think for 1 second that you can get away with not writing it down. Too many silly mistakes happen because we think we're better than just writing it down. Write it down. A is 1, B is 7, C is 6. So when we plug it into our formula, we have a negative 7 plus or minus the square root of 7 squared minus 4 times 1 times 6 all over 2 times 1. Do not skip this step of writing this out. This negative right here causes more mistakes than I can possibly count. Because when we get a negative 4 with a negative 1 with a negative 7, one of these negatives typically gets dropped. So we still have the negative 7 plus or minus the square root of 49 minus, well, let's make sure it's a minus, negative 4. What I do with this is I kind of forget that the rest of the problem is there. I have negative 4 times 1. It's negative 4. Negative 4 times 6 is negative 24. All over 2. X is equal to negative 7 plus or minus the square root of 25 all over 2. Square root of 25 we know is 5, so we have x is equal to negative 7 plus or minus 5 all over 2. And here's where our two answers break apart. So in one case, we have the negative 7 plus 5 over 2. In the other case, we have a negative 7 minus 5 over 2. This gives us negative 2 over 2. That gives us our answer of negative 1. This one gives us negative 12 over 2. That's how we get our answer of negative 6. So quadratic formula was a lot more work than factoring, I grant you that. That's why factoring is still very much important, including getting it to look the way we want it to look. But we'll always find us our answer. So let's try another one, like this. So we have our quadratic formula, x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Do not think you're better than the song or even writing it down. It will help you no matter what. We're going to plug in. Turns out this is actually a negative 7 for b, so we have a negative 7. I know you're thinking, well, why don't I just write down it as a positive? You're going to be writing this down multiple steps. Don't skip one. You're just going to write it down positive the next time. Negative 7 squared minus 4 times 2 times negative 9 all over 2 times 2. So the negative 7 does become a positive. Negative 7 squared is a positive 49. We then have a negative 4 times 2. That's negative 8. Negative 8 and negative 9 gives us a positive 72 all over 4. We then have x is equal to 7 plus or minus the square root of 121 all over 4. So we get x is equal to 7 plus or minus 11 all over 4. X is equal to 7 plus 11 over 4, or 7 minus 11 over 4. So x is equal to 18 over 4, or negative 4 over 4. Simplify both fractions when possible. So 2 goes both into this, 9 halves, or negative 1. All this means, because we have two rational numbers down here, was that this was factorable from the beginning. We need two numbers that multiply to negative 18 that combine to negative 7. It's negative 9 and 2. Sort of, we have one that does this. So we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. We plug in, we get negative 6 plus or minus the square root of 6 squared minus 4 times 1 times 9 all over 2 times 1. We get x is equal to negative 6 plus or minus the square root of 36 minus 36 all over 2. That gives us x equals negative 6 plus or minus the square root of 0 all over 2. Well, the square root of 0 is 0. So either way, negative 6 plus 0, negative 6 minus 0, we have negative 6 over 2, or just negative 3. This was a double root. We know that square roots cannot be taken of negative numbers. So if we end up getting a problem where underneath our radical at some point, so we have 3 plus or minus the square root, and we have 36 minus 39 all over 7 or whatever. 3 plus or minus, the minute we get this negative underneath the radical, we have no real roots. We're going to look at one more example today, one where it has roots, but they're not factorable. So this quadratic here is not a factorable quadratic. 2 times negative 6, that gives us negative 12. There's no way for us to get two numbers that multiply to negative 12 to add to 5. So we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Make sure that your square root covers up all those, because technically they're all underneath the radical. So we end up getting negative 5 plus or minus the square root of 5 squared minus 4 times 2 times negative 6. Oh, this one actually might have some real roots, ones I can work with. 2 times 2, because I kind of solved this in my head. So x is equal to negative 5 plus or minus the square root of 25. Oh, no, it's not. 25. Negative 4 times 2. That's negative 8. Negative 8, negative 6 gives us positive 48 all over 4. So we get x is equal to negative 5 plus or minus the square root of 25 and 48. So that gives us 73 all over 4. From what we talked about yesterday, There's nothing we can do to combine our terms with this radical, but we do have to simplify this radical if possible. So I need to think of perfect squares, 1, 4, 9, 16, 25, 36, such and such, that go into 73. 1 does, but nobody cares. 4 doesn't, 9 doesn't, 16 doesn't, 25 doesn't, 36 doesn't, 49 definitely doesn't, 64 doesn't do it. So none of the ones smaller than 73 work. So this is simplified. And we leave our answer as such. One last thing that we check for. Is there anything in common between these three numbers out in front? The answer is, again, no. There's nothing we can do to simplify this. There are our two roots. If we did end up getting something and say our roots boil down to this, we're going to try to simplify this 24. Four goes into 24. So x equals 4 plus or minus the square root of 4 times 6 all over 8. We're able to take the square root of the 4. So we get 4 plus or minus 2 square root 6 all over 8. We then check, do these three numbers have anything in common? We don't have to worry about the number underneath the radical. It's protected by the square root. 2 goes into all of these. The final answer for this one would be 2 plus or minus the square root 6 all over 4. We know that 2 and 4 have something in common, but because nothing with the 1, we're done right there.